Okay, so we're talking about the second derivative. The second derivative is the derivative of the first derivative. So it's the second derivative of the original function. So if y equals f of x, then some notations we might use are f double prime of x, d squared y dx squared, or d dx of dy dx, the derivative of the first derivative. Now, the question we want to answer is, what does f double prime say about f prime? And then consequently, what does it say about the original function? Well, if f double prime is positive over an interval, then we know that the first derivative is increasing over that interval, because that's what a derivative tells us about its original function. If f double prime is negative on an interval, the first derivative will be decreasing over that interval. So the big question is, what does it mean for the first derivative to be increasing? Or what does it mean for the first derivative to be decreasing? And what does that tell us graphically? Well, if we have a changing rate of change, that brings concavity into our graph. Now our graph will be concave up if the first derivative is increasing, which is also when the second derivative is positive. The reason it's concave up is because the slopes are increasing as we go from left to right. Conversely, the graph will be concave down, or open downwards, when the first derivative is decreasing, which is when the second derivative is less than 0. The reason it's concave down is the slope is decreasing from left to right. So, if the second derivative is bigger than 0 on an interval, the graph is concave up there. And conversely, if the graph of f is concave up on an interval, the second derivative will be positive. We could also say that if the second derivative is negative on an interval, the graph will be concave down on that interval, or open downwards. If the graph is concave down, then we can also say the second derivative is greater than 0. The second derivative is less than 0, sorry. On the graph below, we're going to determine where our graph is concave down. Alright, so kind of follow along with me. We'll use the highlighter here. And so we see that it's concave down, or it opens downwards all the way till about right in here. So that's our first interval where it's concave down. Here we see it's concave down as well. Let's see, we got another interval here where it's concave down. And we got one last interval here where it's concave down. So those highlighted in yellow are all intervals where the graph is concave down. That means those are all intervals where the second derivative of this function is negative. The ones that we did not highlight are all intervals where the graph is concave up. So those are all intervals where the second derivative is greater than 0. Now, the other thing that we have are places where it switches from concave down to concave up. That means our rate switched from decreasing to increasing. We have one right here. Those are our inflection points. So we have an inflection point there. Going to have one about right here. Going to have one right about here. One right about here. We'll have an inflection point right around here, and we're going to have one last one somewhere in this area. Now we don't know exactly where they are, but that's what we're going to learn how to find. Because the graph switches concavity at inflection points. That means, for instance, if we look at this inflection point here, the graph went from concave down, or a negative second derivative, to concave up, or a positive second derivative. So if the second derivative went from negative to positive, then there had to be a place in there where the second derivative was either 0 or discontinuous. So that's going to give us a method for identifying inflection points. It'll be very similar to the first derivative test. We're going to find where our second derivative is 0 or discontinuous and check to see if the original graph changes concavity at those points.